We already talked about the continuity equation for finite control volumes. Essentially, mass in equals mass out, right? And then we're going to start talking about how this applies to a point in space. So this is the natural extension, right? We're going from big control volumes down to little infinitesimally point-sized control volumes. And then the second thing, kind of the second topic of today, is this thing we call the stress tensor, and understanding the stresses that act on a fluid element, right? The whole idea, what motivates most of what we do in fluids is things like conservation of energy, or for this chapter, F equals ma, okay? Newton's second law. So this third bullet point here comes down to starting to figure out what goes into the left-hand side of that F equals ma. How do we write out the forces that act at a point in space on a little particle of fluid? And then we'll segue this into the next lecture and start deriving the famous Navier-Stokes equations. So for those of you that are derivation averse, I'm trying to boil this down as much as possible, but understand that in any fluids class you take, at any university, the Navier-Stokes equations is deriving them is part of the process, okay? Because it comes down to understanding, like, we can't actually solve them, right? What we're going to get out of this at the end of the day is a set of equations where I say, guess what? No one can solve these. There's no existing solution. It's one of these prizes where you get $1 million if you figure out a way, all right? So the real kind of the state of the art in fluids is simply being able to understand them. So quick little recap of last time. Okay. So in the previous lecture, we started talking about fluid element kinematics, right? And we said essentially that fluid motion consists of four. We'll go ahead and say 4 elements or types. The first was translation. Okay, this is simply how a fluid particle gets carried by the flow. So we can say that the rate of translation is the background velocity v. We have dilatation, which is the amount of fluid sort of stretching, if you will. It's the rate of fluid expansion. It can be written as the gradient operator dotted with V. We have rotation, and we thought of as the rigid body spin of a fluid element. Okay, and this can be written as the vector omega equals 1/2 gradient operator crossed with V, which is also 1/2 curl of V. And in addition, right, the other way we talk about rotation is through this alternative metric called vorticity, which is exactly the same thing. It's also the rigid body spin, but this is defined as zeta equals simply the cross product of the gradient operator in V or the curl of V. So the vorticity is simply equal to 2 times the rotation. Okay? It's a silly convention, but it's one that's been adopted across all of fluid dynamics. And then the last one, which is the shear, or the angular deformation. Okay? Angular rate of deformation. And this is defined as gamma dot ij is equal to dvi dxj plus dvj dx okay, where V1 is equal to U, V2 is equal to V, V3 is equal to W, X1 is equal to X, X2 is equal to Y, and X3 is equal to Z. This is what we call indicial notation, okay, where V is just a placeholder for velocity, has 3 components, X, Y, and Z, and X is simply a placeholder for a direction, okay, 1, 2, 3, X, Y, Z. So with this collection of 4 different types of motion, okay, we consider rotation and vorticity just different ways of describing the same type of motion. With this collection of 4 types of motion, we can describe the general motion of a fluid particle, okay, kinematically. This is going to be useful because it's going to come into that A part component of our F equals ma equation that we're going to be putting together, right? So today, we're going to start exploring how these different quantities also go into our conservation laws applied at a point in space. So previously when we described the continuity equation, or conservation of mass, right, is where it started from, we applied this to a control volume, right? So for a control volume, we ended up with saying that dm dt, right, of a system is equal to 0, equal to the time rate of change of rho mass in a control volume plus the integral over the control surface of rho v dot n dA, right? It's our Reynolds transport theorem applied to mass, and we've seen this equation, right? This is what gives us our A1 V1 equals A2 V2 that we've been using all over the place with Bernoulli and flow through pipes and such. So what we're doing now is, instead of considering a large control volume, we want to consider a control volume that can approach a size of 0. All right. So the book has a really long and cumbersome derivation of this. I have a much shorter one that I prefer, but it relies on some, trusting in some vector calculus identities. So the question is, right, how does this apply to a point in space, right, as the volume of our control volume approaches 0? So I want you to consider we'll go ahead and just take this this right-hand side where we say that 0 is equal to, right, ddt, integral of the control volume, rho dv plus cs rho v dot n dA. Okay. Anybody ever heard the phrase the divergence theorem before? Okay, so we're seeing a couple hands, which means it was something you probably saw in vector calc, right? And the divergence theorem basically says that if you take the integral over a surface, okay, a bounding surface of a dot product, okay, or the divergence of, rather, a dot product, that you can write it, of a dot product like that with the normal vector, you can write it instead as an integral of a divergence. So what I mean by that is we can write, okay, if this is our control surface, okay, we've got our volume and our normal vector, right, which points out of the control surface everywhere. Then we can write this quantity on the right-hand side as, we can apply the divergence theorem which says that the integral over control surface of some vector b dotted with the n of that control surface, dA, is equal to the integral over the volume that that surface contains of the gradient operator dotted with b. So if we plug that in, what we get now is that 0 is equal to time rate of change, rho integral of control volume, rho dV, plus integral over the control volume now of rho grad dot v dV. If we assume that our control volume stays constant in time, then we can move this component inside. Oops. And we get 0 equal to integral over the control volume of partial time derivative of rho plus rho grad dot v dV. Okay, so what we have here is a very explicit statement. What we haven't said is we said anything about what size this control volume has to be. There have been no assumptions about that yet. It could be the size of this room, or it could be vanishing down to a infinitesimally small little cube. And so if this is true for any size control volume, what that means is that it has to be true everywhere inside of that control volume. Okay, there's a step in logic where we say if we haven't specified what the control volume looks like, then if this whole thing is 0 regardless of the choice of CV, that has to mean that everything inside that CV is equal to 0. And so we would say true for any control volume. Therefore, dT of rho plus rho V is equal to 0. Now there's a choice in here actually. So this is true, but there is a slightly simpler way. I forgot to do something here. My bad. Actually, in this case, so we need to backtrack for a moment. This is what happens when I stop looking at the notes. B here is not simply equal to V, actually. B is equal to rho V. And so what needs to happen here is I need to move rho V in there. And, okay, dot product of rho V is equal to 0. There we go. Okay, so sorry for that misstep, but this here is what we would call then the continuity equation. And what this says is the same thing that the continuity equation for a finite control volume said, is that the rate of change of density, okay, at a point in space has to be balanced by the rate at which a changing density is being carried through that point in space. Now, there are a couple of other steps we have to take here. So what I missed previously and what I want to focus on right now is the fact that the argument of this gradient operator, okay, so some notes say argument of the gradient is the quantity rho v. Okay. In other words, the product rule then d rho dt plus v dot grad rho plus rho grad dot v is equal to 0. Okay, so this is the same equation we have above. We just expanded out that second term. And I want to recognize this quantity right here. Okay, we've talked about what these two terms right here form, right? And we talked about the material derivative, right? We said that big D something dt is equal to ddt of that something plus v dot grad of that something, right? This is the definition of the material derivative. So if we look at those two first terms, then we can see that rho fits into each of these arguments. We've got rho, rho, and rho. So the most compact way of writing this then is that the material derivative of the density plus v dot grad rho plus rho, there we go, grad dot v is equal to 0. Okay, so again, all three of these boxed equations are identical. It's just in how we choose to slice and dice the terms. Now this is the point where if I haven't already confused all of you a lot, I'm going to confuse you further by telling you that your book is wrong. The book says something, it has a definition of what incompressible flow is. Now whenever it says, assume incompressible flow, what does that mean? You assume about the density, rho. It doesn't change, that it's constant, right? So the book says that your book says rho equals constant for incompressible flow. I want you to consider a case where, let's say we've got a river flowing along, but we have some stuff in that river. We've got some rocks, okay. We've got some logs being carried along in that river. Would you say that the density of the rocks, the water, and the log are all the same? No, not necessarily. So the density here isn't constant. At the same time, wouldn't it be fair to say that assuming your log is not, assuming your log is rigid, and same with rocks, that this is all incompressible, right? So really what we would want to say about incompressible flow is that rather than requiring that the density is constant, we want to say that the density of an individual particle remains constant. Okay. And how do we write the time rate of change of an individual particle? Using this material derivative, right? The big d rho dt. So a correct definition for incompressible flow is one where we say d rho dt is equal to 0. Simply saying that density of a particle remains constant. Now, I don't want you to take this, too seriously and, say, oh, this book is garbage. It doesn't know what they're talking about. They don't even give us the right definition of incompressibility. What they've defined in here is more correctly. This actually defines what we would call incompressible and homogeneous flow. Okay. In other words, saying that the fluid is incompressible and it's the same everywhere. It's a very, I understand why they chose to simplify it, but I think it's an important distinction to make. And the other reason I like making that distinction is because if we say our flow is incompressible, okay, that means that our material derivative of density goes to 0. So we can say for incompressible flow that we can basically send this term here to 0 and say that rho gradient V is equal to 0. We can divide through by rho. Divide by rho, and we end up with expression right here. So this is now the continuity equation for incompressible flow. All right, so we saw this before in our lecture last Wednesday. What this is saying is that du dx plus dv dy plus dw dz is equal to 0. In other words, it can't expand in all three directions at once because that involves a volumetric dilatation. Okay. Now, this is really useful because most of the time, or most of the flows that we consider in engineering, we can at least make a first order approximation that incompressibility is okay. So this also then gives us a tool. If we know, for example, if we know two velocities, this allows us to find the third in a V field. So let's consider an example problem. Go. Okay. So as an example, we're given a velocity field that has u is equal to x squared plus y squared. V is equal to xy plus yz plus z. And we're told that the flow is incompressible. Find W. Okay, so I'm going to give you guys a couple of minutes to get started on this and see how you think you might proceed to find W, or at least to find the set of functions that could describe W. Note, you're going to want to use this equation right here. So to solve this one, there are really two steps. It means we're going to use this equation right here, right, the continuity equation. Which is grad dot v, shorthand. We're going to use our known u and v functions. We're going to find the partial derivatives of u and v with respect to x and y. Set those equal to 0, solve for dw dx. Okay. Then we're going to have dw dx equals something, integrate on z to get w, or at least a set of w's. So what's the partial derivative of u with respect to x? We got 2x. Okay. Partial of v with respect to y. Good. Okay, so what does that leave for us for dw dz then, or partial w, partial z? Heard minus 3x minus z, right? So the next step, right? So we would say this is, step number 1. Solve for dw z. Step number 2 would be integrate to find w. So we've got dw dz is equal to negative 3x minus z. If we integrated both sides with respect to z, negative 3x minus z dz. What are we going to get? Well, this is a fairly straightforward integral. So negative 3xz minus z squared over 2 plus. So here's the thing. This is the point that I want to make. So we got a c, right? So that unknown constant, it doesn't actually have to be a constant. What happens if that's a function of x? Right? Does that still work? Do we still get the same partial derivative with respect to z? What if c equals 3xy plus x minus y squared? Does that change anything? No. So rather than writing c, I'm going to say plus any function of x and y. Okay. In other words, w can be any velocity that includes this dependence on z, and then can depend on x and y at any, in any way that it wants to, and it's still going to satisfy the continuity equation. All right. So the continuity equation is not going to uniquely define it, but it is going to bound the potential set of velocities that work. All right. Okay, we've got one more note here. Now, as engineers, we also tend to like things that are round, things like pipes, pipes, circular containers. I like submarines. So we need to know how to apply the continuity equation in not just Cartesian coordinates, but also cylindrical coordinates. So if we were writing the continuity equation, we'll go ahead and say this, the full form here. D rho dt plus okay. My question for you is, how does this change when we move into cylindrical coordinates? Or rather, does this change? Do we have to change how we write this? No. That's the beauty of using vector notation, is it works in any coordinate system you choose. The only thing that changes is how we would write it in terms of individual partial derivatives. So we would say, the same, right? Vector notation works in any coordinate system. So the only thing that's going to change is the way that we write our gradient operator. Okay? So we would say that rho v is equal to 1 over r d dr r rho plus 1 over r d theta rho d theta plus d dz rho z. And so so if we plugged this in, we could go ahead and write our continuity equation in cylindrical coordinates simply by tacking on, let me move this over a little bit, simply by tacking on our d rho dt plus that is equal to d rho dt. And that's our continuity equation written out in expanded form for cylindrical coordinates. So if we wanted to do, yes?
Do you need the 1 over r in the last term, or do you not need that?
In the dd theta?
In the ddz.
No, you don't. Yeah.
Aren't you doing a material derivative now?
I mean, you can do the material derivative, but this is, I simply, the idea here is that we could write it in terms of the material derivative, but the material derivative itself, right, involves those terms already. So it's, I mean, if you wrote everything out in expanded form, it would look exactly the same. Rather than using the material derivative, I used the first version of the continuity equation that we derived. And then I took that, I said the product rule expands that out. If you group those into, you just group them up differently, you end up with something in terms of the material derivative. And that helps us when we move into incompressible flow. So, so this, right, this version here, so this is valid for compressible or incompressible flow. If we assumed that it was incompressible, right, so we could assume that the material derivative of density is 0, then we would end up with just v equal to 0. And again, we would just simply use this, we'd simply expand this out in terms of our cylindrical coordinates. But I'm going to save you the trouble. Those equations can all be found in the book. All right. Okay. The stress tensor may have to wait for the next lecture. The only thing that I want to, yeah, you know what? Rather than try to cram it in right now, we'll leave it at that. We've covered the conservation of mass at a point in space. On Wednesday, we'll introduce the way that fluid elements push, pull, and shear against one another.